Just a minute. So hello everyone, and welcome to our session today. We have a special lecture today as part of as per Sprint, and this is by Doris. Welcome, Doris. And let me introduce you to Doris. So Doris actually did her PhD at CA Saclay, after which she was a postdoc in IIS Orsay. After that, she went to Japan, where she was a research fellow, moved on for a short while in Portugal, and now she's at present in Marseille. Her research interests are the formation and evolution of filamentary molecular clouds and early stages of star formation, physical properties of molecular filaments and their role in regulating star formation, observations of gas and dust in continuum as well as spectroscopy in total and polarized emissions. So she works basically with observations from Herschel, Planck, Irán-Fati, Nobayama, ALMA, JCMT, confronting observations with numerical simulations and theoretical models. So we all look forward to hearing Doris. And Doris, over to you. To everyone, you can put on your questions in the chat window. And after that, after the talk, which would be 45 minutes, we will have time for Q&A. So please do put up your comments. Thanks a lot. Doris, over to you.
Okay, thank you very much. Thank you for the invitation to participate to these seminars and for the introduction. So today what I will discuss with you, it's related to the structure of the interstellar medium and the star formation that takes place in this interstellar medium. And in particular, I will present you some of the properties of the filamentary structures that we see in the interstellar medium. And these filamentary structures, you can see them nicely, I think, on this very beautiful image taken by the Planck satellite that traces the dust emission of the interstellar medium. And so I would like to, so I hope my presentation will not be very long and I will finish within the 45 minutes. But I think I don't mind if it's more in an interactive way. So if you have questions during my presentation, it's fine for me if you want to interrupt me and ask me the question. So I will like to start by reminding you how beautiful can be a sky during a clear night when we look up the sky and then we see all the stars that fill the sky. And we can see the stars with our own eyes because they emit in the visible light. But what we cannot see with our eyes, it's the matter that fills the medium between the stars. So this medium, it's not empty, it's full of dust and gas. And then we can observe this medium when we observe at longer wavelength. So here you can see on the left-hand side image of the Orion constellation that I think most of the people know. And then on the right-hand side is the same field observed in infrared, and then we can see the matter that fills the medium between the stars. And so this is the interstellar medium that we usually call as ISM. And so this is something very important to remember, that the electromagnetic wave, it's not only what we see with our eyes, but it's very wide. And when we do astronomy, we cannot go in space and then measure the properties of the objects that we see. And so what we do is to use the information that we can get from the electromagnetic wavelength observed at different wavelengths, different frequency, in order to get information of what is out there. And so for that, we use telescopes in the ground, with very different kind of telescope covering different wavelength ranges. And then also we have to use telescopes we are in space, and especially for the short wavelength, the high frequencies, which we cannot observe from the ground, because these are wavelengths which are mostly absorbed by our atmospheres. And then also, of course, for the long wavelength, we have some telescopes in space in order to observe the emission of the interstellar medium. And so here I show very briefly an image observed at different wavelengths, and what you can see is that the galaxy doesn't look the same at different wavelengths. So in the visible, we mostly see the stars. In the infrared and radio wavelength, we see the interstellar medium, so the medium filling the gas and dust, which fills the medium between the stars. And then in X-ray, we observe more high energy radiation, which mostly comes, let's say, from AGN activity or the black holes. And so here I show another image in the visible, where we can see the stars. So each of the dots, it's one star. And then what you can notice in this image, it's patches, dark patches, where we don't see many stars. And so this was noticed a long time ago, in the 1900s. And the question was asked, these dark patches, are they holes in the sky? Are there regions where there are not enough stars, like in other regions? And very quickly, astronomers understood that actually, no, these are not holes in the sky, but there are regions filled by dust and gas, which absorb the short wavelength emission emitted by the stars which are in the background. So that's why when the star emission comes through the cloud and we observe this region in optical with our eyes or with optical telescope, we don't see emission because it's absorbed by the interstellar clouds. And then these clouds, they emit at longer wavelengths. So if we observe with telescope, yes?
Ma'am, so basically dispersion takes place.
Excuse me?
Dispersion of light.
Yeah, it's both. It's you have absorption and then there is also scattering. You're right, but it's both. Yeah. Yes. And then these clouds, they emit at longer wavelengths. And so if we observe at longer wavelengths, we can see them. And here I show an example of interstellar dust, which are micrometer size grains that absorb the light coming from the star and then they emit at longer wavelength. And then if we telescope such as Herschel, then here we can see the emission of this dust grain. And so this image here corresponds to the same image here where we see actually the interstellar medium in extinction. And then here we can in the Herschel image we can see the emission of this matter. And then we can now characterize the structure of the interstellar medium, and then we can see how this structure is organized in filamentary structures. And now we know that these filamentary structures are the exact locations where star formation takes place. And actually, I find these images very fascinating because we can see simultaneously the large-scale emission, the diffuse emission, and you can see the denser filaments. And then in these dense filaments, we can see more the compact and bright emission, which corresponds to the prestellar cores. So they are the initial condition of star formation. And so here I show briefly the sequence, the star formation sequence of solar type star, which start by the gravitational fragmentation of these filaments. And then the fragmentation of these filaments result in a prestellar core, which is a gravitationally bound object. So this is the first step. And then this gravitationally bound prestellar core will collapse under its own gravity. And then a stellar embryo will form in the center. So these objects are called protostars. So they are not stars yet, they are before the stars. And then during this stage, the stellar embryo accrete material from the envelope, while some of the material of the envelope collapses on the midplane to form a disc-like structure. And there is some of the material which is infalling, which is re-ejected by the stellar embryo in bipolar outflows. So this system evolves, and the star in the center continue accreting material till accreting most of the matter in the envelope and also in the disk. And then in this disk, there is also the formation of planets. And then the star, the young star reaches the main sequence and starts burning its hydrogen, and then becomes a star in the main sequence, like our sun, and surrounded by planets which form during this sequence. So here there is an example of a stellar system with a star and the planets, which is similar to our solar system, where our star is the sun, and then there are planets in the surrounding. And this means that the planet formation is a very natural consequence of star formation. And then if you are interested to understand how a planet like the Earth, where life could emerge, have been formed, then a natural step is to understand the star formation process, and also how these filamentary structures are formed and how they fragment, and what kind of stars they can form, depending on the properties of these filaments. So the big question that we ask and we are interested to understand is to understand how these filamentary molecular clouds form and evolve in the interstellar medium, and precisely what are the physical processes that are responsible for the initial condition of star formation. So the star formation sequence that I showed earlier, it's more or less well understood, even though there are lots of details that are not very well described, but the sequence is more or less understood, but the initial conditions are not yet understood, how the filaments fragment and what kind of prestellar cores they will form. And so the third question is exactly what is the role of these filaments in the star formation process? Are they responsible in regulating the star formation? And are they important structure in the ASM or not? So can we understand star formation process without including the importance of the filaments? And as an yes?
Ma'am, but to understand star formation process, you need to understand the role of interstellar filaments. So we have to consider these interstellar filaments.
Yes.
Don't you think?
That's what I think. Yes.
No, because you were saying that, is there any other way of understanding the star formation process without involving these interstellar filaments?
Yes, of course. So
yeah, isn't it but obvious that we need these interstellar filaments? We need to understand the properties and everything.
Yes. So earlier, when like let's say 20 years ago, when researchers have been trying to understand the star formation, the idea was to form molecular clouds, and then the molecular cloud will fragment into prestellar cores, and then the prestellar cores will evolve into stars. But there was no discussion on the the filamentary structure. There was no, at that time, the observations were not showing that the main sites of star formation are particular structures, which are filaments. So there was just a discussion of molecular clouds, which were mostly roundish structure, which were fragmenting to form stars. And now what we started to see about 10 years ago, and precisely with the Herschel observation, was that actually there is a step between molecular cloud and prestellar cores, and the steps in between is filament. And then now we can understand by including the role of filaments, we can understand some of the properties of star formation that we couldn't understand before. So this, it will take some time to explain these differences, but the idea is that. Yes?
I still got the gist, yeah. I still got the gist.
Ma'am, excuse me. Exactly what elements are these filamentary molecular clouds are made up of?
Okay, I will continue and you will have the answer of your question a bit later, okay? And if not, you can ask me again. Yeah, so these three first questions that I was asking were the big question, but we can a bit narrow down these questions and then ask more an observational question, which is what are the properties of the filaments? And so for that, I will just introduce a little bit more what is the structure of the interstellar medium and what are the different phases of this medium. And basically, there is the diffuse interstellar medium, which is mostly made of atomic gas, so mostly H1, atomic H1. And then this diffuse interstellar medium can be warm and diffuse, and then also it can be colder and denser. So it's the cold neutral medium. And then this atomic gas is compressed and cools down, and there is a phase transition from atomic medium to molecular medium, and then there is a part of the interstellar medium which is molecular and mainly molecular hydrogen, but not only. And then these molecular clouds are cold with a temperature of 10 K, and then they are dense. And then there are these molecular clouds. So before they were called molecular clouds, and now that we know that they are filamentary, we call them more filamentary molecular clouds, are the sites where star forms. And so stars formed in this dense molecular cloud, and then at the end of their evolution, they re-emit the material that they form during their lifetime in the fusion, and then they enrich the interstellar medium with new molecules. And then these new molecules, they go back to the diffuse medium, which becomes dense, molecular, and then there is new generation of star formation. So this is the cycle of the interstellar medium. So we can see that we are dealing with different scales and different densities and different temperatures. And more particular for the molecular medium, there are different kinds of molecular clouds. So there are giant molecular clouds, which are like around 100 parsec scales. And then there are inside this giant molecular cloud, smaller molecular clouds, which are about 10 parsec scale. And then inside these molecular clouds, there are the filamentary structure, which are smaller. And then we have the prestellar cores, so the progenitor of stars, which are about 0.1 parsec. So here also you can see that in scales, we are dealing with many scales and also many densities, a few orders of magnitude in densities, and also masses. So in order, okay, so here it's the structure of the interstellar medium. And then also in the interstellar medium, there is an interplay between different forces. So there is gravity, turbulence, and magnetic fields. And there is the interplay between these different forces that make the evolution of matter and formation of structure of the interstellar medium. So in the diffuse interstellar medium, gravity is not very important. And then there is mostly an interplay between turbulence and magnetic fields. But in the dense interstellar medium, so the molecular medium where star formation takes place, there is these three forces are equally important. And so in order to understand the physics, it's very important to treat these three forces simultaneously in order to understand what's happening. And for star formation to take place, so for the gravitational collapse of the prestellar core to happen for star formation, gravity should win over turbulent and magnetic field. And understanding how this process is happening, it's also very important. And these are questions which are still open. We still don't understand how the turbulence and the magnetic field are dissipated for gravity to become stronger, for the gravitational collapse to happen. And so observationally, in order to address these different scales, different densities, and also different physical processes, we need to combine different observational techniques and wavelengths. So for gravity, for instance, we have, in order to know what is the gravitational energy, we need to have information on the density and the mass. And for that, we mostly use dust continuum observation. For the magnetic field energy, we need to know what is magnetic field structure and strength. And for that, polarization observation can give us a hint on that. And for the turbulence, and in order to know what is the dynamics and the velocity structure, usually molecular line spectroscopic observations are needed. And so for the following of this talk, I will mostly present observations of dust continuum and try to explain what are the information we can derive from dust continuum observations. And so for that, I will present a bit the observation observed by Herschel Space Observatory, which is a space telescope launched in 2009. And then it has two detectors, PAX and SPIRE, and then it observes simultaneously at multiple wavelengths. And then these observations are very important because they observe the peak emission of the dust grains, of the cold dust grain in the interstellar medium. So we can well characterize the emission of this dust grain and the interstellar structure, which is formed by this dust grain. So here I show an images of 5 wavelengths towards the same filamentary structure. So from 700 micron to 500 micron. And then here I show an example of the spectral energy distribution for the 5 wavelengths. So here on the y-axis is the flux, and then the wavelengths on the x-axis. And so what we can do is we can observe the intensity at these different wavelengths and model these observed intensities in order to have an estimate of the dust temperature and the column density of the medium. So how much particles we have along the line of sight, which is emitting this light. And so for that, we parameterize the equation with these two terms. So the first one is the Planck function, which is expressed like this and which depends on the temperature. So here I show an example of the Planck function for different temperatures. So for instance, here the 6,000 Kelvin corresponds to the temperature of our sun. And you can see that it peaks in the visible wavelengths. That's why actually our eyes. Yes?
I may interject. Ma'am, what does the Planck function basically indicates? Okay, like what does it tell us when we plot a graph?
So it represents a black body. So it describes
the black body radiation. Are you talking about?
Yeah, it's a black body radiation. So it represents what is the intensity of an object at different frequencies. And so an object that has 6,000 Kelvin will have the peak intensity at around 400 nanometers. And then for the other frequencies, the intensity will be lower. And an object that has 300 Kelvin will peak at a wavelength which is much larger. So basically, that's what it tells you, the black body. And here, when we model the dust emission from the interstellar medium, so we have the black body, but we have also a term here, which is the dust optical depth, which tells you actually that the emission, it's not completely black body, it's gray body. So it's an emission which is modified by the properties of the dust and the number of particles you have along the line of sight. So that's why it's not only black body. So here this plot that I show here is for black body. But what we have in the dust, the emission, it's not black body, it's a gray body, it's modified black body. And so it's modified by the dust optical depth, which can be, which is proportional to the gas surface density and the dust opacity. And the dust opacity, it's given by this relation here, and it depends on the dust properties, basically.
So this dust opacity, is it a universal constant?
No, it's not. It depends on the dust.
Material, on the material, the presence of the dust.
Yes. It depends on the dust properties, and also it depends on the frequency.
Yeah.
Okay. So there are different studies that try to combine different observations in order to have to derive dust models, basically, which are given here. So we know that for the interstellar medium, these values are the ones that represent the best the dust that we observe, but it's always under some assumptions. So then another quantity that we usually use is the gas column density, which is proportional to the surface density that we have here. And so basically, when we have this 4 or 5 wavelengths from the observations, we fit these observations with this kind of function where we have 2 unknowns. We have the temperature, the dust temperature, and then we have the gas surface density or column density. And so then we can do this pixel by pixel towards the maps, all the maps that we observed. And then we can create or derive column density maps and dust temperature maps. So this is here an example that I showed you towards a region which is called IC5146. So here we have the column density. So you can see the brightest area are where the column density is the larger. And then we have column densities of about 10 to 21 centimeter -2, which is more the background area. And then on the dust temperature map, we can see that these filamentary structures, which are very dense, are also very cold. So here we have this Cocoon Nebula, actually, which is a region where there is already star formation going on. So there is already some stars there, or a cluster of stars. And then the star is heating up the medium in the surrounding. And so that's why we see the region, the dust towards the Cocoon Nebula as a warmer region. While in the filaments, there is no star formation. And so actually the interstellar radiation field is shielded up, and inside the filament, the medium is cold. And so so now what we can do is to try to analyze the filamentary structure that we see in these images. And then, so here I show some of the images observed by Herschel within the Herschel-Guth survey. And so there are different molecular clouds, different filamentary molecular clouds, which have different star formation activity. So some of them are forming a lot of stars, like in Orion, for instance, or Aquila, and other regions, like in the Pipe and the Polaris, the star formation activity, it's lower, but they are all filamentary. And what we want to do is to try to describe the properties of these filaments. So there are many different algorithms that have been developed lately to identify and trace these different filamentary structures. And so in the following, I will describe mostly an algorithm which is called Disperse, which gives this blue crest that you can see on this image. So Disperse was initially created developed in order to trace the filamentary structure in the cosmic web, so in a cosmological context. So it's created by Thierry Sousby, and then there is a very nice website that describes how to install Disperse and how to use it. And then when I started working on the interstellar filaments, I discussed with Thierry Sousby, and we adapted his code in order to trace the filamentary structure in the interstellar medium. So that's why I've been using this code. And basically the idea of the Disperse algorithm, which is a very mathematical code, is to measure critical points in a map. So it works in 2D or 3D. So it measures critical points, which are maximum, minimum, and also saddle points. And then when all the critical points are detected, the critical points are connected following gradients, and which means the crests of filaments. And there is one, let's say, the most important parameter for the input for Disperse, it's what is called persistence threshold. So basically, the persistence threshold determines if a critical point it's persistent enough with respect to a given noise. So if the for instance, in this plot, if the persistence threshold which is chosen is 1, then these two persistence pairs will remain and will be traced in an output skeleton. But if the persistence threshold it's larger than 1, then this pair will not pass the criteria, and only these pairs will remain. While in this case, both pairs can remain if the persistence threshold is lower than the difference between the different critical points. And so basically this idea of persistence threshold will define what kind of structures will be traced in a map. And so, for instance, here is an output from Disperse for one of the region for a given persistence threshold, which is in this case 5 times the noise level in the map. And in blue, so you can see the crests which are traced by Disperse. And then after this, there is processing that allows us to identify individual filaments and also remove some structures which may not be very real. And like this, we can identify a number of filaments in the map, and then we can derive their properties. And so here, what I show on the left-hand side is a column density map of a filament. So it's a filament in torus, it's a molecular cloud. And then here you can see the column density, the temperature map. And then what we do is to take perpendicular cuts to the crest of this filament. And then we average the different crests measured at different positions along the crest to derive radial profiles of the filament. So here on the top, it's column density, and then in the bottom, it's temperature. So you can see that how the filament is colder by a few kelvins with respect to the surrounding background. And then here we have the column density profile. And then what we can do, it's to model this observed color density profile. And for that, what we do is to consider that the filament is cylindrical. It's elongated and cylindrical and can be described with such a density profile, which is called plumber-like profile, where the rho c it's the central density and the r flat is the flat inner part, and then here the p it's the power law at large radii. And so at large radii the density decreases as r minus p. And then from this model density profile, what we can do is also to measure the mass per unit length of the filament, which is the mass of the filament divided by the length. And then we can compare this measure of mass per unit length of the filament with a critical value, which gives us actually the equilibrium between gravitational collapse and internal thermal pressure. So if the line mass of the filament is larger than the critical value, which is given here by this expression, then the filament is unstable for fragmentation. If, on the other hand, the line mass of the filament is smaller than this critical value, then even if there are perturbations along the filament length, then this perturbation will not be gravitationally unstable, and the filament will not fragment. And so this has been shown by these numerical simulations where actually the filament, when it has a line mass which is larger than the critical value, and there are some perturbations that are generated in the filament, then the filament fragment into cores. And then this also shows us how the cylindrical geometry is very favorable to the formation of stars, because when the filament is gravitationally unstable and it fragments, the timescale of local fragmentation is faster than the timescale of the global collapse of the filament. So that's why the cores have time to form and evolve and form stars before all the filaments collapses. And so what we can do is to do the same, to use these functions to fit the observed profiles, and then derive the values for the power law slope at large radii and the flat inner radius, which are given here. So for instance, for this filament, the P equals 2, so the density decreases as R minus 2, and the R flat, it's of the order of 0.03 parsec. And then what we can also do is to use a Gaussian fit in order to describe the central width. But this Gaussian fits actually cannot reproduce the power law wing of the profile. So that's why the plumber-like profile is a more appropriate function to describe the profiles of the filaments. And so from the observations, we can also integrate the observed color density profile in order to derive the line mass, and then to compare the observed line mass with the critical value that can be derived from theory for a given temperature, to see if the filament is thermally supercritical or not. So if the filament has a line mass larger than the critical value, for instance, it's the case in this example, the line mass of this filament is 50 solar mass per parsec, which is larger than the critical value, then the filament is thermally supercritical and unstable for gravitational fragmentation. And actually that's what we see here. We see that this filament is fragmented into star-forming cores. And so we can do the same for the same kind of analysis for a large number of filaments that we observe in the Herschel images. So here I show examples of 3 filaments. This filament here in orange, it's a filament which is thermally supercritical and forming stars and has a very large central colon density. The filament in the middle, has a line mass which is close to the critical value. And then on the right-hand side, there is a filament which has a line mass which is much smaller than the critical value. So it's a filament which is not forming any stars. And the result of this analysis is that these three filaments that have different colon densities and different line masses, they all have the same central width of about 0.1 parsec. And so this was a very surprising result, which is also derived from the analysis of a large sample of filaments. So here it's about 600 filaments observed in different regions, in different star-forming regions. And then the result of the analysis of the colon density profiles and the fitting of this colon density profile, as I mentioned earlier, shows that all these filaments, they seem to share the same central width of 0.1 parsec, which is shown here by the orange histogram, while they have a distribution in length which is much wider, which is shown here by the red histogram, and also which have the filaments, they cover a wide range in colon density, which can be seen with the blue histogram, which shows the Jeans length, which is inversely proportional to the central colon density. So the origin of this 0.1 parsec is not well understood yet. And it's still debated, the origin. But one of the interesting idea is that this 0.1 parsec width of the observed filaments correspond to the scale in the interstellar medium, which is called the sonic scale. And it's a scale at which the turbulence, which is supersonic at large scale, dissipates, and at scales lower than 0.1 parsec, the turbulence becomes subsonic. So it means that this 0.1 parsec is the scale where the turbulence is dissipated to form structures of this scale, which are observed as the filamentary structures. And also there are this kind of filamentary structures at the 0.1 parsec scale are formed in simulations where there is dissipation of turbulence. So this gives a hint that the dissipation of large-scale turbulence may be important in the formation of this filamentary structure. And just to finish, I'd like to discuss a theoretical model for the formation of the filament. So this is a new theoretical model, and the idea it comes from a bit the dissipation of turbulence in shock compression. And the idea is the interaction between different clouds which have different sizes and different densities. So the initial condition is a cloud with a given density, which interact with the propagating shock waves. So you can imagine a larger cloud that propagates and interact with this dense clump. And this interaction will compress the dense cloud into a sheet-like structure. And then this compression will also bend the sheet-like structure and the magnetic field, which is frozen in the matter. So it's also organized in the sheet. And this compression and the bending of the structure will generate a flow of matter that will accumulate to form a filament. It's an elongated filamentary structure and perpendicular to the magnetic field.
Ma'am?
Yes?
Ma'am, so your B is basically the magnetic field you're talking about, which forms sheets and they are bent.
I didn't understand the question, but maybe I can finish and then you can ask me the question because I'm at the end of the talk. Yeah, so here on the right-hand side, there are snapshots of the numerical simulation. So from top to bottom, it's evolution in time, and then you have age on view and then face on view. And so there is the interaction of the large cloud with the smallest, more densest cloud. And this interaction will flatten the small cloud. And then in this small cloud, there is filamentary structures which are formed. So here I can show you the movie of it, where you can see that the interaction will actually form sheet-like structure. And then it's in this sheet-like structure that the filaments are formed. And then in these filaments, which accrete material from the surrounding sheet-like structure, the filament increase in mass and then fragment into star-forming cores. So here the blue, basically, they are the location of the stars which are formed. Okay, and so here, so in this talk I only talked about dust emission and the column density structure of this filament, but this slide is just to give you an idea of what we have from other kind of observations. So on the right hand side, it's molecular line observation from the carbon monoxide observation, and the different colors indicate different velocity structures. So in green, we have the velocity of the gas associated to the filament. So in black, it's the crest of the filament traced by disperse. And then in blue and red, it's the surrounding medium, which shows actually matter which is falling onto the filament. So it's redshifted and blue shifted because part of the gas is coming towards us and the other part of the gas is going away from us. But if we have a 3D geometry of what's happening, then we can say that most probably the gas is infalling onto the filament. And on the left-hand side is, so the background image, it's a column density map from Herschel. And then in green, it's the orientation of the magnetic field structures derived from polarization observation. But what you can see is that here, what we see is that the magnetic field structure is perpendicular to the filament. And so these observations are very compatible with the theoretical model that I just explained, where we have matter falling along the magnetic field lines to form a dense filament, which is perpendicular to the magnetic field and along which star formation takes place. So this is my summary. So now with the new observations, mainly from Herschel and also Planck and also other ground-based observations, we can have an information on the structure of the interstellar medium. And then we know that this interstellar medium is filamentary. And then the dense filaments, there are the main site of star formation. And then they give the initial condition of star formation, and the results of the common widths of 0.1 parsec of this filament may give an information on the origin of the formation of this filament. So we need a physical process that will form filaments with a 0.1 parsec width, and also it has an implication in regulating star formation and the type of stars that are formed in this filament. So I didn't discuss about this, but this is undergoing research. And that observationally, the properties that we derive from the data are set strong constraint on theoretical models, and then they are very important in order to understand what's happening. So my last slide is some references that can also complete a bit what I said. So the first three are more on star formation and the ISM and molecular cloud in general, and the last one is more review paper on filaments, the filament properties, and how the filaments play an important role in regulating star formation. So I will stop here, and I'm happy to try to answer your questions. Yes.
Ma'am, do you have any thesis paper which you have written on these star formation or filaments?
I didn't understand. Can you repeat, please?
Ma'am, do you have any research papers which you have written? Have you written any research papers?
Yes. There are loads of them. You can Google it and find using her name.
Okay. Okay.
And he was talking about references of your work. So
yes, yeah. So on the
there's loads of them.
slides, I have some of the references. But if you need, I can give you a copy of the papers if you want.
Yeah, I would love those copies.
Yeah. So
okay, send me your email and.
Okay, ma'am, can you give me your email so I'll send you?
Piyush, what I'm going to do is I will take it and put it up on the website. Okay. So I'll put up her presentation as well as that, right? So Doris, we can do that. I'll take it from you and we put it on the website.
Okay,
so
ma'am.
Yeah. We can access it from the website.
Sure. Yeah.
There's another question, Doris, from Avik. How do magnetic fields evolve in filaments?
Yeah, so I didn't discuss about very much about my magnetic field, but so the idea is here this cartoon shows is first of all that magnetic field is very important because actually the matter and the magnetic field are frozen in. Matter cannot go around as it wants. It has to be connected with the magnetic field. And the fact that the magnetic field structure is the magnetic field is strong makes actually this bending possible. So if the magnetic field was not strong enough, then you would not have this bending, and then you will not be able to create actually a flow along the magnetic field. The fact that the magnetic field is strong, you can have this bend, and then you can have a flow along the magnetic field, and then you will be able to form long filaments. So there are some numerical simulations where they try to vary the magnetic field strength, and then they show that if magnetic field is not strong enough, then you will form more clumpy structures. And in order to have long filaments, magnetic field is important. And then now we are getting more and more observations that are tracing the magnetic field. And then we can see that how the magnetic field structure is ordered, and also how the structure changes inside of the filament when the filament fragments. Yes, so I think this would need another talk to explain the different aspects of the magnetic field, but this is a very interesting and very new research direction, actually, because until recently there were not many observations on the magnetic field, but now starting from Planck and also after that we are getting a lot of new data on this. So now it's the state-of-the-art discussions, magnetic field structures.
Thank you, ma'am.
0.1 parsecs, right? Why 0.1 parsec? There's so much debate about that too, right? Do you think there's something magical about 0.1 parsec?
Not magical, I think. I think it's physics.
Yeah, no, but I think it's like everywhere. It seems to be everywhere, right?
Yeah.
That's what gets it.
Yeah, it's something that is regulating actually what's happening, and I think that so what I described, the idea of the dispersion of turbulence and forming this kind of structure in shock will create 0.1 parsec with structures. But I think what is more complicated to understand is how the densest filaments, they still keep the 0.1 parsec width, because the densest filaments, they will they need to collapse because they are gravitationally unstable, and so they need to shrink. But it's not what we observe. And the idea, it's actually shown in this slide, is it's the accretion. So this these filaments, they are accreting ambient material, and then this accretion actually brings in gravitational energy and also turbulent energy. So the gravitational energy creates turbulence, and so the turbulence create additional support for the filaments. And so the filaments cannot collapse, and then they somehow keep a width of 0.1 parsec. And also there is, of course, the magnetic field that becomes stronger in the filament and then supports this, the filaments, and would give something about 0.1 parsec. So one thing is that numerical simulation, usually they have difficulties to reproduce these observations. So I think there is some physics that is still missing. But
how would you think it relates to the Jeans criteria?
Yeah. Actually, it's shown here. So basically, if the filaments, they are in hydrostatic equilibrium, then they would have a width which is comparable to the Jeans length. So they would have a distribution which is similar to the blue distribution. But actually, it's not what we observe. So which means that these filaments, they are not in hydrostatic equilibrium. They are dynamical structures. For the faint filaments, they are most probably bound by and the external medium, and so that's why they don't expand. And for the densest ones, they must have somehow more turbulence, so more internal pressure that will keep them wider than what you would expect from the Jeans length criteria, which is not the case. So the Jeans length criteria doesn't work for filaments.
Okay, thanks. There's another question. Okay, will the future studies of filamentary molecular clouds reveal new types of stars? I don't exactly understand.
So actually, it's not that they will reveal new type of stars, but they will let us understand what are the type of stars that we expect to see. In other words, what is the distribution of the mass of the cores and the stars that you expect to see. And so something that I didn't discuss, well, maybe I have one slide that I can show. It's this one. So here on the left-hand side, the image, it's a column density image. And then in blue triangles, it's the positions of the cores. So the prestellar cores that are extracted from these images. And we can see here also that the cores are mainly observed along filaments. Sorry. Then here on the right-hand side, it's a plot which is a bit complicated, but I can explain it very briefly. So first, I want you to look at the dashed histogram, dashed curve here, also here. So these are the IMFs. It's the distribution of the masses of the stars. So these are already formed stars. And this initial mass function is something which is it's well described and well observed, but the origin is not understood. So why the IMF peaks at a stellar mass, which is a bit 2.3 solar mass, and why there is a slope of this form. So the origin of the IMF, it's not well understood. There are lots of theories, but it's still debated. And with these observations, what we see is that if we plot the masses of the cores that we observe in these filaments, we can get a distribution which is like this in blue. So it's the CMF, it's the core mass function. And what we see is that this core mass function has the same shape as that of the IMF, but shifted to higher masses, which suggests that actually first you form cores which have this shape in the distribution of mass, and then somehow the mass will go into stars and some of the mass will be lost in outflows and stuff. And then you can end up with the IMF. So these observations kind of shift the problem. We don't want to understand anymore the IMF. What we want to understand is CMF. And this can actually be explained of course, step by step, if we understand how the filament fragments into this kind of stars. So I don't think that we will find new stars, but we will be able to understand what are the properties of the cores that are formed in the filaments.
Okay, so another one, are there small filaments embedded? Are there embedded filaments? What is their significance in forming bigger filaments?
Yeah, so this is also an interesting question. And there are observations. So here the data that I showed is from Herschel observation. So it's what we see, it's the total column of gas that emits, and then we have a given resolution. But if we look inside of these filaments, sometimes we see smaller structures. And then if we look in different observations, for instance, in observation that can trace the information on the velocity, then sometimes we can see that this sum of the filaments, actually there is some connection of different structures and different structures with different velocities. So there is a question of substructures, and this is interesting to see, because also something more interesting is to look at small scales and then see how the cores that are forming in filaments accrete from the surrounding material. And sometimes we can see some filamentary structures also around the cores, which are actually feeding the cores in mass. So it's important to keep in mind the scale we are probing when we discuss about things.
Okay. We have another slightly distinct question. How do filaments behave if there's a black hole somewhere around?
I think I don't know the answer.
If I were to rephrase my question, this is my question. If I were to rephrase it, I want to ask you that when the black hole formation process starts, do these filaments, are there filaments formed? And if there are, how do the properties are? Do they differ from the normal filaments, or are they the same? Do the magnetic fields differ somehow?
Well, it depends. What kind of black hole are you referring to? Are you referring to a stellar black hole?
Schwarzschild black hole, Schwarzschild radius black hole, or maybe a supermassive black hole.
Okay. So if, for instance, if you are referring to a black hole that results from the death of a massive star during the supernova explosion, the energy which is released from the supernova explosion will most probably actually disperse the cloud which surrounds the stars and disperse the filamentary structures. And so there will not be anymore this kind of molecular filamentary structure in the surrounding.
So basically, these filaments they break.
Say it again?
These filaments break when a supernova.
Yes.
Okay.
Yeah, so that's the more discussion on the stellar feedback. So how the stars which are formed in these clouds, and more precisely how the massive stars affect the surrounding medium and ionize the medium and disperse the medium. So that's actually that's something that it's not very much investigated. So how the stellar feedback will affect the properties of this filament. So this has been discussed in terms of clouds, but not in terms of filamentary clouds yet. But this is a very interesting topic as well. So to understand how these filaments will disperse and break up if there is a massive star that is formed nearby, and then the stellar feedback, how the stellar feedback will affect the stars.
Yeah, Understood, ma'am. Yeah.
I don't see any other questions. Is there a question I've missed out? I think I've covered all the questions which are there. Is there any other question which somebody wants to ask? You can unmute and ask or type. So I don't see any other questions. Are there anything else? But Doris, that was a lovely talk. That was a really nice talk. It was very interesting, very nice. And thanks for all the suggested readings and all that. I will share that on the website, and so students can actually access it from there. So do we have any more questions? Does anybody want to ask something else? Or are we done? Yeah, so I think there are no more questions. So let's all thank Doris. Thanks, Doris, so much for a lovely talk. That was really very nice, very interesting. There are lots of people in the chat window saying thanks a lot for the class and thanks for the lovely lecture. You can see the comments yourself too. And it was very nice talk.
Ma'am, would we have any other lectures just like this?
I will. How did you get to know about this one?
Ma'am, actually, my mom's friend, she found it from somewhere else, and I'm pretty interested in this stuff, so she just keeps sending me all this.
Okay, so you can send me mail. I will tell you how to log in.
Sure,
okay.
Yeah.
Okay, yeah. So thanks, Doris. Thanks so much for a lovely talk, and thanks so much for being with us. Thank you very much.
Thank
and
you.
Bye-bye. Yeah, thanks a lot. Bye-bye.
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 Bye-bye.